It's a pleasure to give this presentation to Weblio. Thank you very much for joining. My presentation is on desiccation cracking of clay soils, mechanisms, modeling, and mitigation. And I'm Professor Jayantha Kodikara, Director of the ARC Smart Pavements Hub, a Department of Civil Engineering, Monash University. So today I will cover these topics. First, I'll introduce the phenomenon or observations, then the mechanisms, modeling, and mitigation of desiccation cracking. So phenomenon, as you can see in these pictures, on the left-hand top, clay liners. So soils crack when they dry. So in this example, what you see is a clay liner built in a landfill, which has cracked when it was exposed to the atmosphere for an extended period of time. And this is not desirable because clay liners are supposed to have low permeability to prevent ingress of contaminants into the groundwater. And even when you cover it with a geomembrane or any liner, plastic liner, still it can undergo cracking. Top middle, you see the uplift mechanism for breach formation in UK embankments. And here you can see the formation of desiccation cracks leading to failures. On the top right, you see giant desiccation polygons that have generated over time in geological time scale in USA. The spacing between the cracks is very large in comparison to other cracks you saw so far. In the bottom left corner, you see road pavements, which also can experience desiccation crack effects, especially close to the edges, shoulders of pavements can experience desiccation cracks reflecting onto the surface due to shrinking and swelling soils underneath. Bottom middle, you see so-called Gilgai formations. When you have a land cleared for agriculture and you leave it for a period of time, and if it undergoes wetting and drying, and eventually it can create these landforms, which depressions in the black areas, and the water can get accumulated in these depressed areas, and the Aboriginals, Australian Aboriginals, used to call them waterholes, and Gilgai stands for that in local language. And the bottom right hand, you see desiccation cracks that have happened in mass, and we have worked on this topic to some extent as well. Some pertinent experimental observations. So here I am plotting some results from experiments carried out in boxes, and soil is prepared at wet stage and put into these boxes and subject to desiccation, and cracks emerge, and depending on the thickness of the crack size vary. The higher the thickness of the clay, the higher the crack spacing. As you can see from this diagram, soil thickness on the x-axis, mean area of the cell on the y-axis, you can see as soil thickness increases, mean area of the cells increases as well. In other words, spacing of the cracks increases. And another thing you can see is a bunch of lines here refer to the basal interface, soil and the box material, friction. So if you have more friction at the base, you get different behavior. In contrast to loose or soil, something like glass, which has less friction, you get smaller mean cell areas. So we can see here, soil thickness is very important, base friction and adhesion is very important. Another observation is, if the soil is placed in a container without any frictional resistance at the bases, like greased container, it will just shrink without any cracks. Sometimes it can undergo curling like that, which is due to non-uniform shrinkage. And this picture here shows graphically, as thickness reduces, how the crack size decreases. So significance of constraints or restraints. So here on the left-hand side, you see a plastic container filled with wet soil, clay soil. And the container sides and the base have been greased before placing the soil. Therefore, soil has shrunk uniformly without any cracks. And you can see no internal restraints. Uniform drying, because we dried it slowly. No external restraints, smooth base. Therefore, if we don't have any internal or external restraints, you will get full potential shrinkage, referred to as epsilon SH. And this depends on the soil and the climate. In contrast, on the right-hand side, you see a container where the soil is placed without greasing. So there is friction and adhesion at the base. So external restraint from the rough base, partial potential shrinkage. That means some free shrinkage is restrained by the external restraints. Therefore, you get tensile stress development and cracking, right? And full restraint means no shrinkage at all observed, but cracking suddenly appears. So no strain observed, but cracking suddenly appears because it's an internal stress development. Influence of thickness and restraint and energy. So on these pictures here, you see two clay layers drying on the laboratory bench. First one is 10 millimeter thick layer. It has cracked severely, and same soil placed to 40 millimeter thick layer, the same size container, has undergone no cracking at all. So this shows the influence of thickness, and the stress relaxation at the top or the deformation, which is allowed for thicker layer, releases the stress, and also the energy required for fracture to form is not sufficient for this diameter, for that thickness. So those two coupled together has created no cracking there. Some of the experimental observations, and you can see here, this big diagram or this video shows the cracking in a long mold. You can see crack happens in the middle and then subdivision take place. Each sublayer get divided by subsequent crack. So this is primarily what's called subdivision. And at the end, all the cracks have been formed for that amount of drying in that climate, and only widening of the crack width takes place with further drying. The picture on the left bottom is showing a box of soil cracking. And you can see that one has undergone basically subdivision as well. So here you can see a crack starting from here, from the edges, and then further subdivision. And on the right-hand side, you see potato starch undergoing drying in a box. And because potato starch has certain fracture energy and the particle size distribution, it undergoes cracking simultaneously and shows non-orthogonal crack pattern like hexagonal crack patterns or close to that. So that's formation of crack patterns is a function of the particle size and the energy required for cracking. So mechanism. So what's the mechanism for fracture formation? How does desiccation cracks initiate? When tensile stress exceeds the tensile strength, does it when fractures initiate in desiccation? We mentioned that there is no strain. If the full restraint is applied, you won't observe any strain when the cracks happen. We are normally familiar with seeing strain before cracks initiate. Does it happen when soil desaturates? So these are two schools of thoughts given for crack initiation. But during desiccation, effective stress, interparticle stress, are compressive always. There is no tension for the effective stress. Effective stress can be written as total stress plus suction. And that means total stress is equal to effective stress minus suction. So total stress goes negative if restrained. For instance, zero lateral restraint condition. If you apply zero lateral restraint condition, then there is no movement that can be observed. Therefore, this delta sigma dash or change in effective stress is zero. If it is zero, then delta sigma or the total stress change is minus delta S, and delta S is suction increase. It's a positive quantity, therefore negative. That means delta sigma is tensile. So with further drying, suction increases, therefore delta sigma increases and tensile stress increases, and approximate it reaches the tensile strength at some point, and that can be considered as failure in a macroscopic explanation. At the failure location, however, delta S becomes zero. That means water menisci fractures and cavitation occurs, and that brings down to delta sigma to zero, and cracks emerge and soil particles separate. So basically, fracture in clay soils emerge when water phase breaks. Where is failure likely to occur? Normally, they occur in weak locations, boundaries, large pores, and flows. Flows can be minor cracks that was already there, or stress races such as large angular particles like sand particles, gravels, and so on. Water phase failure occurs, menisci failure, at the point of failure leading to cavitation or air entry. Total stress goes to zero at the locations of cracks, allowing uncracked soil to shrink, compress, strains due to suction. Can we say then soil cracks at the air entry value of a soil? If a soil is drying, like seen here in this graph here, void ratio against water content, saturation line is shown here, straight line. So initially it is slurried soil, so it dries along that line during shrinking and then undergoes residual shrinkage. Without any shrinkage, it undergoes water loss. So normally air entry happens around here, but you can see cracks happen much earlier. Therefore, cracks happen due to local air entry at the locations where it cracks, not at the global air entry of the soil, as seen from water retention curves. Water retention curve will give you this global air entry, but local air entry can lead to desiccation cracking even when it is saturated. So that macroscopic explanation of desiccation cracking can be represented in graphical form here. Tensile strengths against time. So during desiccation, tensile stress builds up in green curve, but tensile strength also builds up, and eventually they cross over, and one could consider cracking to initiate. Fracture formation requires to consider fracture energy, because a formation of a surface during fracture requires energy. So what is this energy for soil? So here we have the fracture energy against moisture content. So you can see the moisture content is high, like saturated slurry kind of soil. Your fracture energy is very small. And that approximates the fracture energy of water, like surface tension based fracture energy of water. We actually measured it using this device, ring shear apparatus, restraint ring shear apparatus, to measure that. And it approximates the fracture energy of water. And as you get soil dried, your fracture energy remains very small until such time it starts to increase exponentially. So this exponential increase is related to the plastic or frictional energy required in formation of a crack tip area. Because when suction goes up with the drying, your frictional energy required around the plastic crack tip also goes up. So basically you can explain then total energy of fracture energy of soil is water fractional energy, particle which are separating energy, and GSS fracture energy due to soil plasticity. The first two are relatively small, and this one, GSS, is the one which increases it exponentially. Modeling. How do you model this process? Theoretical modeling. So theoretically, Morris et al. Initially explained we could use elastic theory with unsaturated soils, lateral stress that develops during suction increase can be explained in a restrained environment in this fashion. So when suction increases, sigma x becomes negative because this component is going high. So you could develop some equations, but parameters are modulus and this H modulus against suction. However, they are elastic properties. We know these properties change significantly as soil dries, and it's a highly nonlinear process. Therefore, alternative approach is needed. And we use the incremental representation of stress development. Tensile stress increment is a function of modulus, tangent modulus at the time, times effective strain. That strain is given by observed strain, that's the true strain observed, minus the free shrinkage. If there were no restraints, then what would have been the strain? So, for example, if full restraint condition, your observed strain will be 0. Therefore, you will get your tensile stress development maximum, because this is 0 and minus this times that gives you the maximum tensile stress development for full restraint condition. If there is free shrinkage, observed strain will be same as the free shrinkage strain, and these two are equal. Therefore, 0 will give as the tensile stress development. No tensile stress will develop in free shrinkage, no cracking, therefore. So this approach can be incorporated into stress analysis in finite elements or finite difference as a residual stress that can be added to other stress increases due to external stresses if you have them, and then solve for the deformations. And then you could simulate desiccation cracking. This is one way of doing it. So as I mentioned, modeling of fracture development can be approached in a number of ways. Linear elastic fracture mechanics has been tried as well. I mentioned the limitations there of the linear elasticity because the process is highly nonlinear. Then cohesive fracture development is also something we developed, and discrete modeling is another approach. In cohesive fracture modeling, we used fracture process zone where fracture opening is here, but fracture goes beyond that and up to a point where virtual crack tip, where tensile stress is present as the initiation of crack. So traction or tensile stress and the crack opening can be presented by this cohesive model, and the energy, fracture energy, is the area under the curve. So utilizing that, and you can present a numerical approach to incorporate fracture formation. In fact, in this particular paper, tensile and cohesive fractures both are catered for, because in desiccation, mostly you get tensile, but some instances you get cohesive shear cracks as well. Global modeling approaches. So hybrid continuum discrete element method with cohesive fractures, also using JUDEC program, has been used. Then FEM with mesh fragmentation has been used. Discrete element method has been used, and smooth particle hydrodynamics, or SPH, particulate method has been used. This is an example using mesh fragmentation technique by Marcelo Sanchez et al. 2014. And you can see he has simulated 4 millimeter, 8 millimeter, 16 millimeter layers. And you can see the subdivision process and the crack formation. And you can see the effect of layer thickness. As layer thickness goes high, your crack area also goes high, your spacing goes high. So that is in match with the phenomenological observation I mentioned earlier. So you can capture these processes using these techniques. So further topics in desiccation modeling that you need to consider: coupled thermal moisture flow deformation, or THM, utilization of unsaturated soil continuum models, net stress-based or effective stress-based, wet-dry cycling and environmental stabilization is a concept, and we can see how that happens. Field applications and simplified methods for design against desiccation cracking. So these are some of the topics one can pursue for future research. Field fracture model results. So this one shows in a field, if we simulate a suction profile and increasing in suction, surface suction of S here, how much cracking we will get in a particular soil. So here, depth of cracking against the fracture energy. So if fracture energy is ignored, 8 MPa cracking at the surface will give you something like 2.5 or 2.6 meter depth of cracking. If you have 10 meter, you get higher, close to 3. And then if you have even higher, the crack depth will go up. But if you have fracture energy incorporated, your crack depth will decrease based on the amount of fracture energy. So as you can see, the influence of fracture energy is also clear. Mitigation. How do you mitigate desiccation cracking? So I will use the equation I presented earlier. So increment is tensile stress. It's a function of modulus times the effective strain. Effective strain is observed strain minus free shrinkage strain at the same conditions. So in order to reduce mitigation, you want to reduce free shrinkage. So how to reduce free shrinkage? You can reduce fines, because fines are the ones which shrink. Large particles like sands and gravels, they don't shrink, aggregates. So reduce fines, or use less shrinking swelling fines, or introduce angular aggregates. They will interlock and stop shrinkage. Increase density. If you increase density, then you can reduce free shrinkage. Increase creep. So if you increase creep, your stresses will relax, right? So use slow setting binders, such as slow setting cement. So on the other hand, you can reduce the restraints or increase the observed strain. So reduce the friction at the base. So free shrinkage can take place more. Reduce moisture loss using a seal. So you can see here, moisture loss is important. So if you can reduce moisture loss by putting a seal, you can reduce the stress development and potential cracking. So cracking potential can be given by this equation. So you have free shrinkage, effective shrinkage divided by failure strain. Effective shrinkage is epsilon shrinkage minus creep shrinkage, so together, and the failure strain. So here you can see alpha delta W can be taken as a moisture content change, moisture loss. This alpha is a material property given by all these properties. So alpha is a function of those things. And failure strain is when soil fails. So if you have fibers or rubber and things like that, you can increase the failure strain and reduce the cracking potential. Or you can reduce the moisture loss or use these to reduce alpha. No point increasing tensile stress alone, because when you increase tensile stress alone, your modulus also increase, and these failure strain drops. Therefore, that's not of value. You can use plastic fibers. In this picture here, you show using plastic fibers, you can reduce cracking. Unreinforced soil without plastic fibers undergoes crack. As you increase the crack percentage with or length, actually crack length here, you can get no cracks and only micro cracks occur. Micro cracks are more favorable than large cracks because water flow and other things are hindered quite significantly when the crack width is lowered. So that's one way of reducing desiccation cracking. So references I have presented are given in here. So you can use them to download the papers. And thank you very much for your attention.